Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video is going to deal with how to undertake an F-test to test for the difference between two population variances. So I suppose what we want to do is we want to try to figure out whether two samples that have been randomly selected, whether they've been drawn from populations that have different population variances. This particular test is very important because it allows us to choose between two possible alternatives for our independent samples t-tests, where we want to test for the difference between two population means, and in particular the two variants of them. The first is where we assume that the samples have been drawn from populations with equal population variances, and the other variant of the t-test where we assume that the samples have been drawn from populations with unequal population variances. So as I said, this video is going to deal with the F-test, which is going to allow us to figure out which particular version of the independent samples t-test we should go for. Or more importantly, and in general, it's going to allow us to test whether two population variances are different based on two pieces of sample data that we've drawn from the populations. Okay, so let's assume we've conducted an experiment. Okay, we have two samples. Okay, that have been drawn from populations. Okay, so we have two samples drawn from a population. Okay, and let's say, for argument's sake, that the sample data 1. Okay, so sample 1, the data is as follows. Let's say x bar, the sample mean for sample 1, let's say, is equal to, let's say for argument's sake, is equal to 35. The average spend of students was €35. And let's say that the sample variance, s squared of 1, let's say is equal to 5. In other words, the variance is €5 on average, or the standard deviation is the square root of 5. And let's say the sample size for our first sample was equal to, let's say for argument's sake, 12 people were selected. They're the characteristics of our first sample. And let's say our second sample, sample 2, that was drawn, has a mean value of, let's say, €46, has a variance, this is 2, subscript 2, has a variance, let's say, of €11, and let's say the sample size in this particular case, sample size for our second sample, let's say is equal to 14. There was 14 observations. In a later video, what we're going to do is we'll use these two pieces of evidence, or these two sets of sample data, to try to infer whether there's a difference between the average of each of these, whether there's a difference between the means that these particular samples have been drawn from. But in this particular video, we're just going to test whether the variances that we've observed, the sample variances that we have observed, whether there's evidence to suggest that these particular variances are associated with different populations, or whether they're associated with the same population. In other words, whether these variances are the same. Okay? From a numerical perspective, we can see that there's a clear difference between them, but from a statistical perspective, taking into consideration the sample sizes and the evidence, is there a real difference between them? Okay, so the procedure for an F-test, so our F-test procedure, okay, once again, it's a 5-step procedure. Step 1, we define the hypothesis. The hypothesis is a statement about the population parameters. In this case, the null hypothesis is going to be that the populations, or that the samples have been drawn from populations that have equal population variances. In other words, that the variance of sample 1 is equal to the variance of sample 2. And the alternative hypothesis is going to be that these two variances are different, okay? That the two variances are not the same, okay? That the two population variances are different. So that's our hypothesis. We assume the null hypothesis to be true until our evidence suggests that that's not the case, and that we can reject the null in favour of the alternative. The second stage is that we choose a significance level for our test. The significance level, our significance of our test, and let us just choose an alpha is equal to 0.05, and let's just keep in mind that this is a two-tailed test for us to show that the two samples have been drawn from populations that have different variances. Okay, All we need to show is that one of the variances is less than the other, or the other is less than the other. So we've got two ways that we can actually prove this. Okay, so our significance is 0.05, and this is a two-tailed test. Now, the F-test can be undertaken as a one-tailed test, where we hypothesize that there's a specific, I suppose, direction with respect to the differences. But for our purposes, it's going to be a two-tailed test, and this is the test that's going to allow us to differentiate between whether we're going for an independent samples t-test assuming equal variances, or an independent samples t-test assuming unequal variances. So we've defined our hypothesis. We've defined the significance level associated with this particular test. Stage 3 is to define our test statistic. And what we know is that the ratio of variances is modeled by an F distribution. So the test statistic is going to be F is equal to the variance of the first sample, divided by the variance of the second sample. Or actually, let me call this the variance of sample A divided by the variance of sample B. Now, the way we've set up our F tables in our formula and tables booklet, okay, we've just given areas, probabilities for areas in right-hand tails, or critical values associated with right-hand tail areas. So from our perspective, what we're going to ensure is